Hello everyone. This is Professor Munir from Department of Chemistry, Aligarh Muslim University, Aligarh. I am going to take up this photochemistry course. Uh, Whenever we are talking about photochemistry, it is the interaction of light with the molecule. This is a introductory uh, introductory lecture where we are going to talk some initial aspects of photochemistry. In coming few slides, I'm going to present which light is important to bring about photochemical reaction. It is the mainly UV light, and what happens when we shine UV light to a molecule, how much amount of energy you are giving to a molecule, what happens when you give this much energy to a molecules, and so on and so forth. So in next few slides, this slide represents the electromagnetic spectrum representing different wavelength. This is the region where uh, the uh, the UV region ranging from 200 to 400 nanometer. When we give this much light to a molecule undergo electron orbital motion. This UV region is again divided into three regions: UVA, UVB, and UVC. The most powerful region is the shorter region, 200 nanometer, and then slightly higher at 280, and then 315. So when we give when we shine UV light to a molecule undergo electronic excitation. What are the different type of excitation? N to pi star, pi to pi star, and sigma to sigma star. It is also important to note that when we give when we shine UV light ranging from 200 to 400 nanometer, how much amount of energy in terms of kilocalorie per mole you are giving to a molecule? I have just jot down the relationship between the wavelength with the energy in terms of kilocalorie per mole, and you can see the 200 nanometer is equivalent to 140 kilocalorie, and then we go to higher wavelength 250 to 114 kilocalorie, and so on and so forth. So when you give UV light ranging from 200 to 400 nanometer, we are giving approximately 63 to 143 kilocalorie per mole. I have in the next slide, I have also shown the amount of typical energy associated with some covalently single bond compound, just to make it more just to emphasize that the UV light is more than sufficient to bring about electronic excitation of different bonding or bonding molecules present in the molecule. For example, CH, the typical energy is 95 kilocalorie, CO is 88, and then CC is 83, and so on and so forth. So 200 to 400 nanometer, which is equivalent to around 70 to 140 kilocalorie per mole, is more than sufficient to bring about different electronic excitation in the molecule. These excitations are, we have, this slide shows, we have a bonding orbital, sigma bond, we have a pi bond, and n bond. So these are electron occupied orbitals. We have anti-bonding orbitals, the pi star and sigma star. So when we shine light, the molecule undergo n to pi star excitation, pi to pi star excitation, n to pi star, and sigma to sigma star excitation, depending upon the different what type of chromophore present in the molecule. The molecule on absorption of light goes to an excited state. Say for example, molecule in S1 state on absorption of light goes to an excited singlet state. These excited singlet states are high energy species, can undergo different radiative and non-radiative processes, or can come back to a higher lower energy excited state, that is triplet. T1 excited state. This is the most simplest simplified version of the Jablonsky diagram, where the S1 on absorption of light goes to S1, S0 on absorption of light goes to S1, and then S1 come back to T1, and then so these excited states can undergo different radiative and non-radiative processes. The dotted line shows the non-radiative processes such as S1 coming to T1 via intersystem crossing, S1 coming to S0 via internal conversion, or T1 coming to S0 also via intersystem crossing, or a radiative process like fluorescence, S1 going to S0, or T1 coming to S0 by radiative processes through fluorescence and phosphorescence. This is the these are the fate of excited state, showing different the radiative and non-radiative processes. These excited stars are high energy species and short-lived. The lifetime of the excited singlet system varies from 10 to power minus 9 to 10 to power minus 6 to 10 to power minus 5 second, and T1 is around 10 to minus 3 second. So you can see here the excited tubular cells are long-lived and can undergo different photochemical reactions. This is, as I have mentioned, this is the most simplified version of Jablonsky diagram. This shows the because we know that the excited vibration levels can have a different vibration level. Ground state can have a different vibration like V0, V1, V2, and each vibration level can have a different rotational levels like J0, J1, and J2, and so on. And same as each excited state can have a E1 can have different vibration level V-0, V-1, V-2, and so on. And each excited state can have a different rotational levels like J-0, J-, and so on. So molecule on absorption can go to excited state, can go to S1 state as well as S2 state as well as S1 state, and then it can come back to defined state. This is the energy levels of different excited states. So molecule from S0 can go to either S1, or it can go to S2, or it can go to S3, or it can come back to a high energy level T1 and or T2 and T3. So this slide shows the level of excited singlet state as well as excited triplet state. As I have mentioned in the beginning, that the molecule on absorption of light goes to excited singlet state. These excited singlet states are high energy species, short-lived. They can undergo different radiative and non-radiative processes such as fluorescence and phosphorescence, or intersystem crossing or internal conversion, and come back to ground state. Or it can undergo different photochemical reactions depending upon the type of chromophore present in the molecule. For example, molecule contains carbon-carbon double bond, can undergo cis-trans isomerization, or cis isomer can undergo 6-pi electron cyclization to give phenanthrene type cyclization. Similarly, starting molecule is a carbonyl, can undergo type 1 reaction, or if there is a possibility of gamma hydrogen, can undergo type 2 reaction by abstracting gamma hydrogen by excited carbonyl to give you 1,4 diradical. So molecule in the ground state on absorption of light goes to an excited state. These excited states are high energy species, short-lived, can undergo different radiative and non-radiative processes, or can undergo different photochemical reactions depending upon the type of chromophore present in the molecule. This photoexcitation can be brought about by two ways, that is direct photolysis, means molecule can absorb light and goes to an excited state, and for this lambda maximum is important because so that we give the proper light, or this excitation can also brought about by indirect excitation, is also called as a sensitized photo reaction. For this indirect photolysis or a sensitized photoreaction, we use another molecule is known as a sensitizer. Sensitizer on absorption of light can go to an excited singlet state, or it can come to excited triplet state, and this excited triplet state can transfer energy to molecule A, and molecule go to an excited state, and sensitizer come back to ground state. So in other words, the molecule A has gone to excited state, not directly via absorption of light, but via a second molecule which is known as a sensitizer, which on absorption of light goes to excited singlet state, and then to a triplet state, transfer energy to give and to bring the A to excited state, and then sensitizer to the ground state. Few commonly used energy transfer sensitizers are carbonyl compounds such as benzophenone, acetophenone, or acetone, and so on and so forth. The indirect photolysis can also be brought about by electron transfer reaction. So, for example, the sensitizer on absorption level can either transfer energy, as I have mentioned in the previous slide, or it can transfer electron to molecule A. The molecule A absorbs accept electron to become radical anion, and then sensitizer becomes radical cation, or in other words, is called it is a donor acceptor photoinduced electron transfer reaction. So as mentioned over here, so we have a two molecule A and D. A is an acceptor, D is a donor. In the presence of light, the acceptor accepts electron, becomes radical anion. Donor donate electron to become radical cation. Few examples of donor acceptors are represented over here. So you can see few the amino derivatives of ethylene, highly electron rich species, aromatic hydrocarbons such as anthracene, the alkyl substituted benzene, and then N,N-dimethyl aniline. These are all can act as an electron donor. Highly electron rich species can donate electron and can become a radical cation. The few representative examples of acceptors are shown over here. This electron tetracyanoethylene is an electron acceptor. 9,10 dicyanoanthracene can accept electron, and then such as hexachlorobenzene and trinitrobenzene. These are few representative examples of electron acceptor which can accept electron and can generate radical anion species, and hence can undergo photoinduced electron transfer reaction. These photoinduced electron transfer reactions are again two types as mentioned here: homogeneous photoinduced electron transfer reaction as well as heterogeneous photoinduced electron transfer reaction. Homogeneous, as name indicates, both donor and acceptors are soluble in the medium and is a single phase reaction. A heterogeneous photoinduced electron transfer reaction is a biphasic reaction where one phase is soluble and other phase is not soluble in the solvent medium, and hence the reaction takes place on the surface of the reaction. One representative example of this heterogeneous photoinduced electron transfer reaction is shown over here. Is a heterogeneous semiconductor such as titanium dioxide, cadmium sulfide, zinc oxide, and so on. So these are few semiconducting materials. The most characteristic feature of this semiconductor material is considering this as the at the surface of the semiconductor, which is characterized by filled valence band and vacant conduction band. There is a band gap energy, and when we shine light of energy equal to or greater than band gap, there is an electronic excitation from filled valence band to the conduction band, and when we generate electron hole pair. And then, or in other words, this on the surface it can generate oxidation and reduction sites on the surface reaction. So these semiconducting materials are not soluble neither in water nor in nor in organic solvent, and hence is a biphasic reaction and can bring about surface reaction and can act as a heterogeneous photo-induced electron transfer reaction. If this area of chemistry has attracted a lot of attention from environmental scientists, where they have used this for photo remediation or photo detoxification of wastewater. And for example, if this titanium dioxide on the presence of light can generate electron hole pair, or in other words, if we do the reaction in the presence of oxygen and water, oxygen pick up this electron, can generate superoxide radical ion, or it can donate electron. Water can donate electron followed by loss of a proton to give hydroxyl radical. So in other words, we are generating superoxide radical anion and hydroxyl radical anion in the medium, which are highly reactive, can react with organic and inorganic toxic component, and then degrade to organic carbon to inorganic carbon such as CO2, nitrogen to ammonium salt, phosphorus to phosphates, or in other words, it can be used for detoxification water. It has a lot of implications in the environmental point of view, and but in other words, they can also bring about heterogeneous photo-induced electron transfer reactions as well. As mentioned in the beginning, that these excited states are high energy species and short lived. They are not only in the molecule in the excited state, they also undergo structural changes as well. For example, this is the say formaldehyde is planar in the ground state. On absorption of light, can undergo n to pi star excited state. These n to pi star excited states are no longer planar and they are perimeter in structure. So what would like to mention here, that the molecule in the excited state, they are also undergoing structural changes as well. Similarly is the alkene, which is planar in the ground state. On absorption of light can undergo pi to pi star excited state. They are also has undergone structural changes and planarity is lost to pyramidal structure. Not only that, there is a bond along when the alkene in the ground state, which has a bond length of 1.34 electron volt, 1.34 angstrom. On absorption, light goes to excited state. The double bond character is lost, and there is a change over from bond length from 1.34 to 1.44 and excited singlet state, and then to a triplet state to 1.58 angstrom. So we can see that when the molecule goes to an excited state, they are approaching towards a carbon-carbon single bond structure, and you can see that the ethane, which has a bond length of 1.34 angstrom, is very close to the excited state of the singlet and triplet excited state of alkene. So in other words, molecule in the ground is on absorption and goes to excited state. They are high energy species, short lived. They are not only high energy, they also undergo structural changes as mentioned over here. In coming new slides, I just want to show you that the photochemical reactions can be brought about in a special photochemical reactor, because normally normal glassware like conical flask, beaker, round bottle flask, they are not used because it can reflect lot of light. So special photoreactors are used for photochemical reactions, so that we achieve a very good conversion of photoreaction. So this is a immersion well photochemical reactor, which consists of a inner jacket and an outer jacket and a light source. Inner jacket, it goes inside and it is water cooled. It is a double walled. We can bring about water in, water out, because when the lamp is on, it's also gets heated up. So in order to avoid any thermal reaction, we need to cool these reactors so that no thermal reaction is taking place and reaction takes place exclusively photoreaction. If we just combine this whole reactor, it looks like this. You can see this is the whole setup. This is a inner jacket, and then the solution comes in between the between the two jacket, and it can be we can also flush nitrogen, so as well as oxygen, whatever environment you use, and this is water cooled. And when the light is on, the reactors looks like this. This is a immersion well photoreactor with light on, with water cooling, as well as some opening for circulating bubbling air or bubbling nitrogen, so that you can bring about reaction in the inert atmosphere, or if you need oxygen, you can also bubble oxygen as well. Other reactors which are also known available to carry out photoreactions are Srinivasan type photoreactor. This is a circular jacket where we have a tubes, and these can have a tube in all around. You can keep your irradiation vessel in the middle, and then which can also have the water circulation to avoid thermal reaction as well as bubbling for this. So this is a second type of photoreactor which can be used to bring about, to carry out photoreactions as well. Thank you.